Okay, welcome back. Let's start the second half. Here's again a summary of really important key points about ordinary differential equations that I already mentioned. And now let's dig into specific examples. I will proceed from simple to less simple and more complex. So we start with one component systems. So one component systems. That means basically you have in mind exactly my two motivational examples, the Ginzburg-Landau theory and the game theory problem for a two-player game. That means our dynamic variable is just a single variable u, and I want to study its time evolution. That means our nonlinear function is some arbitrary function of u of t. And it can also be a function of control parameters. And let's for now just say we have one of those control parameters. You could have more. A one-component system has one dynamic variable, but of course it can have many control parameters. Think of an Ising system where one control parameter is the temperature, and the other control parameter is, for example, the external magnetic field. Okay? So here let's just say we have one control parameter that we call mu, and f is some nonlinear function. Now let's calculate in the way that we just draw. So let's try and see what we can infer from these equations without a line of algebra. So you have a nonlinear function f of u, and it can look, differently. Let me draw something like so. That's an example, of course. You could have many more zeros, and you could have a more rugged landscape as you like as a function of u. But let's start with something that has 3 zeros. Now, what do we know about the time evolution of that system without solving it? Well, if you look here at the equation of motion, if f is 0, then dtu is 0. So f equals 0 for points u star. Those are fixed points of this equation. You could also call them equilibria or reactive equilibria, but that depends on context. Here, for our general mathematical discussion, let's just call them fixed points because they're steady states of the nonlinear dynamics. And those are obviously those 3 points here that are the zeros of that function, right? But they are qualitatively different if you look at them. And that you can also read off without doing a line of calculations. So what's the function f here on the right-hand side? It's positive, right? That's kind of obvious. And here it's negative. So that means if I again look at the equation of motion, on the right-hand side, u needs to increase because the function f is positive. So if I draw the flow into this diagram, the flow goes that direction. And here on the left-hand side, because it's negative, the flow goes this direction. And that means our point here that I drew at 0 is a fixed point, but a very subtle fixed point. Minor changes in deviations from that will make it flow away from that fixed point. So it's an unstable fixed point. And by convention, we draw this as an open circle. It's an unstable fixed point. The system in the long run will not end up there. It will go to the right or go to the left. Now what about those 2 points here, one on the right and on the left? If I again look at my function, it's becoming negative for large values of u, and that implies that the flow has to be backward. So this point here becomes a fixed point where any deviation from it will make it relax towards it, so it's a stable fixed point. Yeah, and convention is that we draw this as full bullets. And the same is true here. As you convince yourself, here is positive. That means the flow goes this way. So that's, again, a stable fixed point that you have there. So it's very simple, right? So you can tell the outcome of dynamics from drawing the function f of u. And the reduced manifolds the system converges to is either that value or that value. The system is bistable because it depends on where you start. If you start with something greater than 0, you'll end up here. And if you start with something smaller than 0, you end up there. There's no unique fixed point in the sense that you always arrive at the same solution. Okay, now that you have that, we change our control parameters. So let's vary this mu here. And this mu can have different effects on the function. It could shift it to the right and to the left, but then nothing much would happen in terms of structure, since you still would have 3 fixed points, and 2 of them would be stable and 1 would be unstable. Something changes qualitatively if you start shifting this curve up and down. So in your mind, just shift this curve here down. And as you shift it down, these 2 points, they will merge together until at some point they vanish. And this will be roughly, so if I draw it, at a point like so. So this is now, you change mu in a certain way. And now things are different because that point still is a fixed point. But those 2 fixed points, they have been colliding. And at this point in time, they actually vanish, just in this point of the parameter mu. So that's a critical value of mu at which you have a qualitative change in the flow in your phase space. 3 fixed points to 2 fixed points. So here we have a bifurcation. And this bifurcation has a name. It's called a saddle node bifurcation. Okay. Now when you think about curves for a one-component system, just imagine drawing any kind of curve. As you change parameters, the typical thing that's going to happen as you change parameters is collision of these kind of fixed points. Right? So these saddle node bifurcations, they are general, they are generic, one says, for these kind of systems. That's the generic case. And you can work this out formally just by saying, let's take a function and let's assume it has fixed points, and let's make a Taylor expansion around that. And then you will see, as you make Taylor expansions, this is the only typical case that you find when you study bifurcations. There's one other thing you can do. You can draw this differently. So we have written it this way. Now let me write it this way. Need a different symbol, V of u. And of course also depending on mu. And so instead of drawing the function and looking at this as an ODE problem, I imagine there is a potential landscape, like the free energy landscape that we had in the first half of the lecture, and the time evolution of the system is downhill on that landscape V, because I have here a minus sign. And of course, if you have a representation like so in one component systems, you can always find the integral, whose derivative is f. You can do so either if you have the analytic expression by finding the corresponding function, or you can just do it here pictorially by constructing graphically the corresponding landscape. So what this is, as I integrate that, this is basically this. Okay? And you'll see if you take the derivative, you go back to the above curve. And now there's another way of thinking about this. Now it's a time evolution in the landscape. So this here is an unstable fixed point. Things will fall off from the maximum of a potential landscape by minor perturbation. That's a metastable, a marginally stable point. While these points here are the ones that the system falls into, and they are stable fixed points, because any deviation from those fixed points will drive you back to those fixed points. So it's very important for 1D systems or one component systems. This is always equivalent to a landscape problem. Is this true in 2 dimensions in general? Question to you. You shake your head? No? Why not? You can have cycles, and that's something you know from electrodynamics. In electrodynamics, if you study E and B fields, there is the Helmholtz decomposition, saying that each vector field can be decomposed into a gradient of a scalar field and a rotational flow. Right? So in higher component systems, this will not work in general. It could work. And for thermodynamics, it's by construction always working. Because there you say you start from a free energy landscape and you have a time evolution in the free energy landscape. So the equation of motion is always derived from a landscape like so. But a general non-equilibrium dynamics problem, like a game theory problem, does not have to have such a landscape structure. Okay. All right. Now let me go a bit deeper into those saddle node bifurcations. Now from a more mathematical, analytical point of view, and what this will amount to is to look into normal forms. With normal forms, there's something specific meant to it when you talk about the dynamic system theory that you study in math, and you can look it up if you like. But basically, a normal form is the simplest representation of a saddle node bifurcation. So the simplest function f you can write down that in itself encodes all the features of a saddle node bifurcation. And you can kind of envision that graphically from this thing here and taking it as graphical elements. So all you really need is that you have to have a collision of fixed points. So you need a parabola. That's all you need. You need to shift up and down a parabola to get all the essence of a saddle node bifurcation. So the mathematical normal form of a saddle node bifurcation is typically written as minus mu plus u squared. So as I said, as a parabola opening up now to the top, where mu is shifting the position of the parabola along the y-axis. So let me draw this in terms of pictures. So here we have our function f. Here we have the variable u, and the same here for all the graphs. I can have different forms. I can have my parabola just like so. Well, then all the function here is positive, and that means the flow here is just going all the way to the right, and the only really fixed point is infinity. That is for mu being less than 0, so the abscissa being positive. There is a bifurcation point where you do have this parabola touching the horizontal axis. That is for mu equal to 0. And that's a particular point because you go there, then you become slower and slower and slower because that's actually a fixed point, right? But then if you kick it a little further, it will continue on going to the right-hand side. So it's flowing into from one side and flowing out of it from the other side. It's not the same as an unstable fixed point, which would have two directions flowing out. Here you have one in and one out. It's just the bifurcation point for this analysis. So this is our critical or threshold value for the control parameter. And then we do have this scenario where we have the parabola being with its minimum below 0. And then we do have this here as a stable fixed point, and that here as an unstable fixed point. Okay? You can see this again from the signs. That is mu being positive, larger than 0. Okay, that's my graphical analysis. And now let's do it in terms of a more analytical way by really writing an expansion around the fixed points. Okay, so let's say that u star is a fixed point. That means f of u star equals to 0. And then consider small perturbations, and let's call them delta u, and that's u minus u star. And I only want to learn about the behavior of my system in the vicinity of a fixed point. So I would like to know how is the time variation of a perturbation with respect to a fixed point. Well, that's easy to say, right? I just need to perform a Taylor expansion on the right-hand side. The first term that you would get is f of u star, but that's 0. Okay? So we start from f of u star, but that's 0 by construction. the next term is the linear term. So the slope of my function f, so plus f prime, that's how I would like to denote it. So a prime indicates derivative with respect to the argument, which is the dynamic variable. That's u in our case. Fu star, f prime u star delta u. And then you have terms which are of higher order, and they will be of order delta u squared. So this is very trivial in this particular case, but it's very general in concept. So what you do is you reduce the complex nonlinear dynamics problem into a linear algebra problem. Here it's a linear algebra problem for a scalar variable, which is particularly trivial, but think of a high-dimensional space. In a high-dimensional space, I can still look at fixed points, and I can still look at deviations from that fixed point, but then you will have a Jacobian characterizing the deviation from that fixed point, and then you need to study the eigenvectors and the eigenvalues of the Jacobian, just like in quantum physics, to learn about the stability of that fixed point. So here let's just stick with this very simple example and do the algebra, just that you have seen it once. And I'm sure you can do this for yourself. That is defined as the partial derivative of f evaluated at u star. And as you do the math, right, this is just 2 u star. And if you insert the solutions, so the fixed points, right, if you look at f of u to 0, this is plus or minus square root of u of mu. So this will be plus or minus 2 times the square root of mu. And now, if you read the equation of motion, this is the eigenvalue. And the eigenvalue negative means it's stable. This is where the slope is down of this function. And as you see here, that's the stable fixed point. If the eigenvalue is positive, the slope is up, like here on the right-hand side. That's the unstable fixed point. This is called, in general, a linear stability analysis, and we will see a lot of that because it's the characterization of stability of fixed points and, in general, more difficult manifolds. This is trivial here, super trivial here, but believe me, once you have a higher dimensional space, even linear algebra becomes quite sophisticated and complicated. Okay? You'll see. All right. Good. That's as far as I want to go for this very simple case. And I want to close with drawing the bifurcation diagram. And let me put this here up in the corner because it's the summary of what we have. So we do have the control parameter mu, and we have the solution u. And this is what's called a bifurcation diagram, illustrating what is the solution and what's the nature of solution as a function of control parameters. We have the threshold value, mu c, and if we are below that threshold value, nothing is really stable. So there's nothing to draw here. And then out of the blue, right at this particular point here, I do have the emergence. So as this touches here, I have the emergence of a fixed point. And this fixed point, as soon as it emerges, it splits up into 2. So out of the blue comes something that has a stable branch and it has a unstable branch. And the way I drew it, it's the parabola, and that's generic because in the Taylor expansion, this is what you get typically. It's called a co-dimension 1 bifurcation because you control one parameter, mu, to create a bifurcation. And in general, you say something has co-dimension n bifurcation if you need to control n control parameters to reach that particular type of bifurcation. Give an example. The temperature is a co-dimension 1 control parameter for a phase transition. Phase transitions are actually co-dimension 2 because physically you can change temperature and magnetic field. So you need to fine-tune the magnetic field to 0 and then change the temperature in order to see a proper phase transition into a magnetic state. Okay. So co-dimension is equal 1 here. Good, let me give you this. Okay, so in general, you will see that in the problem sets, there's exercises, and some of those exercises already have solutions. So read the lecture notes and we'll see. And they're meant to be for you such that you can check and see a full solution. There will also be tutorials in these lecture notes where I don't give the solution, but those are easy things to do. And they are meant for you to actually really do in order to see by reading the material and listening to my lecture whether you've got the point. So they're really checkpoints for you, benchmarks for you to gauge whether you can follow the material or not. And then in the problem sets, we have actual problems. They are not that trivial. And there you can try yourself out, and you will get the solution then later on. Okay? That's the idea of how I constructed that. All right. Now let me continue with another class of important bifurcations. They are called Pitchfork Bifurcations. And there's various ways of writing those pitchfork bifurcations. I write them in a form which is proper for you as people coming from physics. So I will write them in terms of a potential. And I will have two potentials, one I call plus, the other one I call minus. And let me now also write them. So I'll use the same notation. Let me use U to be consistent here with notation. So let me write it in a way that we already discussed. U squared, U to the fourth. Those were the Gainsbourg-Landau fields phi. Now I just call them U. And I consider the parameters for the U to be fixed. It's just a choice. I make this to be 1 plus or minus 1. And the parameter here I call R over 2. And now, sorry for that, but it's easier here to change convention and call the R minus R as compared to the Gainsbourg-Landau problem, just to have a control parameter that has non-trivial behavior for positive R instead of negative R as you have for a phase transition. All right, so that's a potential now. And with that potential, which is a double well potential, you can write an equation of motion which is just the derivative of these potentials as a function of U equals R times U minus or plus U to the third. So from a double well, we go to something that's n-shaped by taking the derivative. That's also very generic in these one-dimensional problems, that those n-shaped objects, functions appear as you look at the equation for u in terms of a nonlinear function. Now let me draw this again. So let's study the cases f v plus equals minus r over 2 u squared plus 1 over 4th u to the 4th. And now start from something that looks like so. That is now for r being negative, right? So I changed the signs. Now there's only one fixed point. As I change r going to 0, the parabola will open up to the bottom, but the u to the 4th term will still pull you up at the ends. So this will have this double well structure. And the feature of this is that as you start changing the control parameter, let me put this here as well. So here, as you have u star as a function of r, what you will have as a solution is first, for r negative, that's the only solution, and this is the branch you have. And now as you go through that bifurcation, well, what happens? You get 3 zeros, you get 3 fixed points. One of them is unstable, and the other 2 are stable. Okay? So that stable fixed point here turns into an unstable fixed point, and at the same time you have the emergence of 2 stable fixed points along the way. This we call a supercritical bifurcation. In the theory of phase transition, that's called a second order phase transition, because the order parameter changes in a continuous way as you go through the phase transition. So it's a continuous phase transition or second order phase transition. So continuous or second order phase transition. And super means because it's above a certain point that the thing has critical features. Good, let me now do the same kind of analysis for the other function, which is the function v minus. And I guess I don't have to write it out. Now I've changed the sign of the u to the 4th potential, and that has dramatic consequences, right? Because now, when you are at a value of r being negative, you of course still have the parabola opening up to the top, right? That's still the case, but the u to the 4th term now pulls you down. So that's the structure you get, something going up and then down, right? And if you now change the control parameter r from being negative to being positive, both of the coefficients are negative, and that means the structure that you will get is something that then opens to the bottom. So what you still have is, when you compare the two, for r less than 0, there's one stable fixed point, but then you can go off if you go over the barriers. And then here for r positive, there's no fixed point. Well, there's this one at 0, but it's unstable. There's no stable fixed point left, really. And this is what's meant also by first-order phase transitions, right? If you have the phi to the 4th term being negative, I cannot have a stable fixed point and no stable thermodynamic equilibrium. I need to come up in the Ginzburg-Landau expansion with a higher order term, with a phi to the 6th term, and here a corresponding u to the 5th term, in order to find a finite stable fixed point there. All right, I don't write this down, but this is a subcritical fixed point. So this is called a subcritical fixed bifurcation, sorry, not fixed point, bifurcation. And the corresponding bifurcation diagram looks different. So now we do have a unstable fixed point, a stable fixed point here. It turns to an unstable fixed point, right? So we are here. That's unstable. And as I said, I need to come up with a higher order term such that this here moves up again at some point. This is due to terms which are in the potential terms that go like u to the power 6, or correspondingly u to the power 3 if you if you go to the corresponding differential equation. Okay? So this then here gives the structure that looks then, maybe I have it here as well. So the structure is then different. So instead of having now as we drew it, the structure is that you have this one stable fixed point, and then you have a subcritical pitchfork bifurcation where you have this structure with an unstable fixed point there, as opposed to a structure where you open up to the top. Now let me illustrate that with the Ginzburg-Landau theory, so you see what I mean. Let me guide you through, and that's something which I take and then close. So let's draw a potential landscape for such a scenario where you have a potential that has phi to the squared, phi to the 4th, and phi to the 6th term. Sorry for calling it x now. The u here has a negative sign in front, the v is positive. And now let's start at different values that you have here. So let's start at RC1. So at values larger than RC1. Then you have a landscape which has just a single minimum, right? That's where you are in the paramagnetic state. And now you start changing the control parameter R, meaning in a magnetic system you lower the temperature. And as you lower the temperature, there will be a threshold value that's called RC1, where here on the sides you have these plateaus that emerge. And that's a bifurcation that happens where now, after changing R even further down, you get two side minima in addition to the minima in the middle. Those are now metastable states, because in thermodynamics you're looking at the absolute minimum of the free energy landscape. So the system would still reside here in this kind of minimum and not be pushed over to the side minima, unless there's some kind of fluctuation, some push that gets you over the barrier. That's a bifurcation point in the sense that you now have those two minima in the system that happen at the sides. And that's a saddle node type of bifurcation. And now you start lowering the value of R even further, and you notice there's another critical value called RC2, where now the side minima are equal height as the minimum that you have in the middle. And now things really change thermodynamically, because as you lower R even further and go deeper into the low temperature phase, the side minima are those that have the lower free energy, so the system will flip and go to the thermodynamic ground state, which are the side minima. Okay? This point is still there, right? That's not gone yet. It's still a metastable point, and if you prepare your system right here, it will not easily go into those minima, because that needs to go over an activation barrier before it goes there. So in general, you remain actually in this point, despite the fact that to the right and left you have lower free energy minima. And now imagine going even further down in temperature, then at some point the minimum that you have here at the middle will cease to exist, and you have things bending down instead of bending upward. And now that point no longer is a metastable fixed point, it's an unstable fixed point, an unstable thermodynamic equilibrium, and any small perturbation will kick you off towards the sides, and those will then be the thermodynamic ground states.